Hi, everyone. Welcome. Thanks so much for joining us today. We're going to have an informal conversation about undergraduate research. I'm joined here today by two summer scholars that preve- uh, participated in undergraduate research with us in the summer of 2024. And they're going to get to share some of their research and their pathways. What we'd like to do in our time together is to talk a little bit about the Robotics Institute at Carnegie Mellon University, some of the research here, but our main topic will really be about how to get into research. What are some of the experiences that Leo and Owen have had? And, how do you get on that path? Each of us are coming from many different spaces, and we want to see how to get started together. So in the chat, you're welcome to ask any questions. We'll take a break from this presentation in just a few minutes. And as we switch over, and I'll also be checking the chat and sharing that information. So welcome, everyone. I'm Rachel Burson from Carnegie Mellon's Robotics Institute. I co-direct the Robotics Institute Summer Scholars Program, and applications are not opening soon. They are actually open. So this is a really great opportunity to come and to participate. What is undergraduate research? What is an REU? So REU stands for Research Experiences for Undergraduates, and RIS is a research experience for undergraduates from around the world that are attending universities as full-time undergraduate students to come together to conduct research with top faculty and to really be part of a research team. What sets the Robotics Institute apart from many other schools and places is that it was the first academic department in robotics in the United States and is one of the very largest robotics research groups affiliated with a university in the world. There are over 60 labs as part of just this department. So coming to the Robotics Institute is a really special opportunity to explore a wide range of research and applications, to get to meet with folks from around the world, to share ideas and to look at the future of robotics, AI, computer science, and engineering. So this is what gathers us, is that we have this focus and we want to explore what's possible in careers for robotics, AI, computer science, and engineering. And that's what's special about RIS. So our goal is to not be a research experience for undergraduates, but instead to be a undergraduate research learning community. What does that mean, and what is the difference there? Well, it means that we're a structured program where we're coming together, and in addition to the research, we have intentional goals to help to build bridges into graduate school here at Carnegie Mellon, at other top universities in the US and in other places in the world as well. So, what does that mean? If I wanted to describe RIS very succinctly, three parts to it. It's a learning community with guided research, professional development, and summing that all up, the environment and the culture is one of mentorship and hopefully a nurturing environment. So, the guided research, we're going to hear from Leo and we're going to hear from Owen about their projects. When you look at the risk program, when you look at other REU programs, you'll see the type of research that scholars are working on. And a great place to learn about the projects and the work within the Institute is to go to the RIS website and to look at the research posters, videos, and papers from the last several years. Start with those posters. They really give you a great snapshot of the research, and Owen and Leo will talk about that. You're coming in and building from research projects. You're going to be part of a team, and the projects are usually customized to your background. So we've had students in each cohort that maybe have just completed their first year of college. Others are in their third or fourth year. And some summer scholars will actually come back for a second summer with us as well. A second part, and I think Leo will especially talk about this, is the professional development. So as one of our commitments, we try to explore robotics and other research, and we host a program called RoboLaunch. And Leo was the scholar lead on that, and it's a way to share and have conversations with researchers from outside of CMU and other places and share that with the world. And then finally, when I look at Leo and Owen, I think about the teams that they came from and what that culture was, and each of the scholars have a very different culture within the lab. And so we'll talk about that some as well, about what is it like within the overall institute. So Carnegie Mellon University is a top-ranked global university located in Pittsburgh, Pennsylvania. There are 7 different colleges that are part of Carnegie Mellon University. We are within the School of Computer Science, and our academic department is called the Robotics Institute. And with that, I'd like to invite my colleagues to share their experiences with us and to talk about what is it like to be a summer scholar and what is the research that is possible when you're here with riss. And I believe Leonardo Santos is going to be the first speaker today. So welcome, Leo.
Thank you, Rachel, for the introduction. Yeah, well, hi everyone. Thanks for coming. I hope this will be helpful for you. I'm Leo, or Leo in Portuguese, as you heard Rachel saying impressively, pronouncing impressively well. Um, and I was a risk scholar in 2023 and 2024. I worked in 2 different labs, and and as Rachel mentioned, I also led the RoboLaunch team. I'll talk about RoboLaunch in a second, but I wanted to start briefly talking about my research project this last summer, and then after Owen presents his work, we'll I'll talk also talk about my journey coming from Brazil, and well to RIS and CMU, and well hopefully some of you will be able to benefit from take some insight and benefit from this. So I'll share my screen. I have my poster here. Uh, can you all see my screen? Can you see my screen? Okay, I'll just go ahead and
Yes,
start. And
that's great.
okay, great. Okay, so this was my work. This was where we were at the end of the summer, at the end of RIS in mid-August. We then continued working on it, and well, have a more complete version that I'll share later, that was submitted to ICRA. It's a robotics conference in September. But I'll talk about my summer project here. If you're interested in seeing the more kind of complete work, complete version, I can send a link in the YouTube chat. So basically, the motivation behind the work was that safe controllers in robotics, they often assume that the robot knows beforehand what's safe and what is unsafe. What we wanted to do was to relax this assumption and allow the robot to infer here motivation to infer from the human user new new unsafe things that the maybe the user maybe it's a user preference or something that the is not contained in the map. And the example that we have here is that a same constraint can be safe for someone or unsafe for another person. So suppose that you have a vacuum cleaner robot in your home, and you have a very expensive rug, or a rug that's very special to you, that's like 100 years old. You got this from your great grandfather, and you don't want your robot to drive over it. But other people, they're fine. They're fine with the robot driving over their rugs. So what what I'll what our pipeline allows in this example scenario is for the user to tell the robot with natural language to do not drive over my rug, and the robot would then infer this using a vision language model, a neural network, and update its safe controller to guarantee that it would avoid the rug. And for the safe controller, we use Hamilton-Jacobi reachability, which my advisor Andrea Baichi studied a lot during her PhD. But basically, Hamilton Jacobi reachability it gives you a policy that says if in each state, if you can think in each point of the map, it tells you whether you can do whatever you want to do to complete your task, say reach point B from A to B, or if in that state you have to use a safe control to avoid going into your unsafe set. So if you're getting close to the rug, then your safe policy from HJ reachability will take over and kind of steer the robot away from the rug. This is basically how it works. Um, so our key contribution here was combining this safe controller based on Hamilton-Jacobi reachability with this online updates from natural language. And for this, we used for the failure set inference from language, use a vision language model. So the humans tells the robot, "Do not drive over my rug." And when the robot sees the rug, the vision language model finds the rug in the image and adds this to the map as unsafe states at unsafe positions, let's say. And then we use warm start updates of the safe controller to be able to update the safe controller online, because you have to solve like partial differential equations to get this controller, which is very computationally intensive and it takes long. So using these warm start updates, you're able to update this in like a few seconds online. So our method has this basic two components. We first offline compute the warm start safe controller that we use for the efficient updates later, and online we have the our vision language model in this orange box. We used an open source model, OVIT from Google, and we combine this with the warm started updates of the unsafe controller as well as it's shown in this like diagram. So the map is constantly being updated, combining the output from the visual language model, and I mean we use the output of the visual language model to as an input to the safe controller, and we constantly update the map of unsafe states, which is the output of this blue box, this safe controller. And we had this with this kind of this demos in simulation. So we first tested using MPPI, which is a well-established planner in robotics. And as you can see, the robot, as expected, completely ignores the rug, because for MPPI, which is just a planner, it just wants to go from point A to point B. It doesn't care because it can't drive over the rug. It's not like a wall or a couch where it would crash. It's just a rug. So it completely ignores the rug. But using our safe controller, you can see that as the robot gets closer, the controller takes over and steers the robot away from the rug. The rug is highlighted in this yellow orange bounding box, and here you can see the advantage of using the warm start updates. We got the first thing that's important. If the map doesn't change, in other words, if there is no new constraint from the user, uh, i- i- the controller is essentially just querying the last update. So it doesn't have to recompute everything. That's why it's zero most of the time. And when the robot sees the rug, or the human tells the robot as the language input to avoid the rug, we need 1 second to update the controller. Whereas if you do not use warm start at all. You have to recompute the controller every time, and it takes a while, like 4 seconds. 4 seconds because this map was small, but it can be, and we it was simple, small, and but it can take longer, like 30 seconds, 40 seconds. Uh, yeah, but that was basically it. Well, I hope it made sense. We have some like cooler stuff in our more complete work, like some hardware demonstrations that I think that are really cool, and some more comprehensive analysis if you're interested. And if you're interested in working with Andrea, for instance, it might be a good resource to look at because you have a really good idea of her research vision and interests. Yeah, yeah. So, and since this was her first risk, I think the more material you have, the better. So I'll be happy to share. Okay, so I stopped sharing screen unintentionally, but I was already done. Uh, yeah, that's all from me, I guess, from this.
Wonderful. Thank you, Leo. And we can talk about the other research project when we come back. We'll give Owen a chance to share his research from the summer. And so you've been with us for 2 summers and so had various different projects. And Owen, do you want to share your research that you worked on this summer?
I was muted. That's what I was. Hello, I'm Owen. I was here last summer, so 2024 Risk Scholar. I worked with Dr. Katya Sakara's Advanced Agent Lab. Let me see if I can find my uh, research poster here. There we go. Are you guys able to see that?
Yep, we can see that. Yep.
All right. So the problem that we addressed is planning with human feedback. So in AI, there's kind of this dichotomy between neural approaches, such as neural networks that use these latent spaces to encode information, and then symbolic AI that uses more like formal logic, Boolean logic, to give a grounded, guaranteed correct answer to a problem with respect to some set of constraints. And the problem is that all of natural language processing essentially falls into that kind of neural realm where you have these not necessarily ground truth, but approximations of whatever language you're trying to learn. And so transformers fall into that domain, for example. So like GPT, and you can talk to that and understands natural language. However, it's unable to provide, if you ask GPT-4, for example, to create a plan to achieve some kind of complex goal, it'll give you something that looks correct, but there's no guarantee that it is correct. And in situations that are very high risk and time sensitive, such as planning a response to a natural disaster. That was our main use case. The Office of Naval Research kind of came to Dr. Sakara's lab and asked him to create this planning assistance agent to help human planners in these complex, high-risk situations. And so my risk project over the summer was bridging the gap between those neural representations and symbolic planning. Um, Existing research on the subject kind of concluded that LLMs alone are not enough to get to that kind of grounded planning as they're not able to reliably self-correct. And so what we did is we used a large language model to create an initial guess of a set of constraints based off of user feedback. For example, a plan could be you need to go from some dock past some debris through either a north waterway or a south waterway to rescue this stranded ship. And the user gives some additional constraints. You need to go through the south one, you can't go through the north one. So the LLM attempts to translate that user feedback into a symbolic constraint. We run a planner, get a plan back, and then we use a genetic algorithm to take that initial set of constraints created by the LLM and create a lot of copies of it that are slightly modified. And then we use a very small LSTM based model to go through this set of nearest neighbors to the LLM's initial guess and determine A, was that initial guess right? or B, if it's not, which one of the similar constraints that we just kind of randomly created is correct. And we found that using the genetic algorithm to explore the space of constraints that are nearby to what the LLM initially guessed improves the success rate substantially. In cases where the LLM's initial guess was wrong, the genetic algorithm was able to correct that mistake 88% of the time. So that's a pretty substantial improvement. And we're still working on this. This is not much data. We're collecting more data right now. But that's pretty much the summary of the project that we're working on. Yeah, I would love to take any questions if there are any in the comments. I know I went kind of quick and might have used a little bit too much jargon.
No, this is great. This is great to get started. One of the things that I have a question about for each of you um, is think about through the eyes of your research progression, right? And so maybe, Owen, first question for you is that this research is very complex, right? There's a really large team that, so the project is complex, it has many components to it. And so this is a great example of research progression, right? So it wasn't your first research project and such. Can you tell us a little bit about how you drew upon prior experiences to prepare yourself to contribute here, and why doing this research and getting this experience will be helpful to prepare you for your next steps, which may include grad school, right?
Yeah, so definitely. So the funny thing is that it's actually not just research experiences that I found myself drawing on a lot. Like most of the research that I've published in the past, at the end of the day, this is kind of like a systems architecture paper where I kind of came up with I mean, you see we have a flow chart here of this is a system built using technologies that and concepts that already exist that achieves a certain goal. And throughout all the research I've done before, last semester I worked with our autonomous vehicles lab at my home university to build a framework for testing cooperative driving algorithms on different vehicles, and that was just like a software framework. And in previous internships, I've built systems that use generative AI, much like this. As a matter of fact, one of the technologies that I used to build this as kind of like a scaffolding was this Python package called LangChain that I used extensively while I was working at Morgan and Morgan and at my own company. So it's really not just prior research experience, but just prior experience in the field of computer science and software development in general. And just the more you're in the field doing projects, whether that's a research project as an undergraduate or an internship or a personal project or a class project even, as long as you're getting experience working with building stuff with code, especially if that code uses AI and you're interested in AI, then, I mean, whether you know it or not, you are building experience that can allow you to pivot into research.
That's really, I liked what you gave so many different backgrounds and experiences. I heard about class projects, I heard about internships with in industry and also entrepreneurial activities. And what really struck me is that in each of those activities, you're building your skills, you're getting um, more insights into it, and that build one thing upon each other. So if you're thinking about research or, a path forward, it's not one thing. It's not like, okay, if you don't have this, then you can't do it.
Exactly.
Instead, looking at it as almost an overall system, like you were saying that the systems design.
Mhm.
What are some of the topics in robotics that you're really excited about? Robotics or AI? Like, what are some things that are really exciting that you think that you know, folks might consider exploring, or, whether that's for their more advanced research or even just to get started? What are some ideas there?
Yeah, definitely. So, the main topic, honestly, of my statement of purpose is this focus on embodied intelligence. So, I've done a lot of work until riss. Pretty much all of my work has been on pure AI. I've done work with like knowledge graph completion. But then as I started to work with AI, this kind of intersection of taking these intelligent systems and seeing them come to life in robotic bodies is like mind blowing. I think the probably the coolest thing in robotics right now is taking these language models and all these different kind of transformer models in general that go from sequence to sequence and seeing how you can apply those to solving the problems of allowing these robots to reason and achieve complex tasks in the real world. One specific, kind of niching down a little bit, one specific thing that I've been working on recently is this kind of idea of merging spatial and semantic perception of an environment. I know LiDAR sensors are a common sensor on robots, as are depth cameras, and you can build these spatial representations. And so you have spatial perception on the one side, and then you have other models that can take in a 2D picture and embed each pixel in it as like a semantic vector saying like, this is a couch or this is a table. And combining those two things to get kind of a 3D representation that incorporates spatial and semantic data, and then seeing how we can get models to understand that, I think is a very important step towards fully autonomous systems. I mean, we humans are able to, have spatial and semantic perception unified, so it just makes sense that it's the next step.
Beth, what are your thoughts, Leo? So, about the directions, things that you're really excited about, and are there questions that you have for Owen about his the research that he did this summer?
Oh, so my interests they intersect Owens a little bit. So there's been this hype on embodied AI and using foundational models for like AI embodied intelligence because yeah, they do perform surprisingly well and allow us to do things that we really didn't think were possible. But these models are still very difficult to interpret mathematically, to describe mathematically. And like I'm not a computer science major, I'm electrical engineering major, so I've been training to do a lot of math and physics, and I like to see equations and see how things actually work, not just like yeah, trying and error and see, oh, let's tweak these parameters and see if it performs better. So like my interests is they kind of combine these two things. Like I want to work on providing like mathematically grounded safety guarantees for those systems, but those learning enabled systems. So that's basically it. So instead of just relying on heuristics or that things will just work, I want to like work on providing actually like yeah, just principled approaches to yeah, guarantee safety in these systems. Uh, and there's also a question about Owen's work, but what was the question again?
Oh, she was just asking if you had any questions about my poster.
Yeah.
Oh, fun thing. I was next to Owen in the riss poster presentation, so
Yes.
I did hear him present his poster for like a lot of people for an hour. So like, I'm probably one of the people that's most familiar with his work.
So one of the questions that came through from participant is that what is the specific method used to detect objects in real time? Is it more like YOLO, where you have to train the model per object before you run?
Yeah, that's a good question. So this comes from the VLM. The VLM is a like stands for Vision Language Model, and it's a neural network that combines vision and language. So it receives one image and one language command as input. So say for instance, let's use the same example of the rug. If I give the network an image of a rug and a word, like just the word rug, it would detect the kind of give me the bounding box of the rug in the image. So those models they are called open vocabulary because they are training such a huge amount of data that's kind of like you don't have like just a small limited class of object that you can like detect as like I, I was going to say old models, but old are like 2015, 16. It's not that old. But yeah, they call open vocabulary because they can detect pretty much anything because of yeah, it's just training on an unimaginable huge amount of data. And it's open source and you can use it for free. It's called AllVIT. It's uh, open world language vision transformer. I think that's it. If you wanna like Google it.
For both of you, um, Owen and Leo, were there things about the what stands out if you had to describe the risk experience with two folks, how would you describe it?
So I would describe it as definitely something that pushed my ability as a researcher. And I say that in comparison to other RU programs, actually, because the summer before this, I was an intern at the University of Tennessee's RU program doing quantum work.
Mhm.
And I found that their approach to involving the students in research was a lot more hands-off. I saw my professor, my research mentor, I think like once a week there. And a lot of the time, I was just working my second job, to be
Mhm.
completely honest. Whereas at riss, I was in the lab every day. Everybody was in the lab every day. I saw Dana on a daily basis. We got
Mhm.
coffee. And I mean, they said 40 hours a week. It was 40 hours a week that I just ended up working to get the project complete.
Mhm.
And that wasn't a bad thing, of course. I mean, I love doing the research, I love doing the work, and kind of being part of this large scale project was something that I was didn't have access to at UCF. I mean, this is a big Office of Naval Research project with multiple stakeholders and other grad students working on it at the same time. So it wasn't just me. I got to have this experience of really being like in a top level lab. That's really what it was. That's what I would describe it as.
And you know, one of the things Carnegie Mellon is known for many topics and with so many strong departments here, there's something about RI that it is massive, right? And then one of the things that's really nice about riss is that there's multiple islands that connect us together. So you have your lab and you have that lab culture. We also have, you know, the learning teams within riss. You have the larger cohort, and then you have alums and other things. And there's so many different ways to explore, and that's what we hope we're able to accomplish together. There was a last question for Owen, and then we'll wrap up. We're a few moments over here. But Owen, how does the project perform under new situations where they might not have trained on or available, etc.?
So the large language models are able to adapt pretty generally. I mean, we use GPT-4 for this. So if you give it a new scenario and ask it to guess at the correct constraints, it'll create a guess that makes sense. It might not be right. I mean, that's yeah, like I said, that's the point of the project, that it might be incorrect. But the reward model that we use to rank the outputs of the genetic algorithm, in the case here, we did train it specifically for this waterway task, but the process that we used for converting the environment description into the training set is something that's repeatable and doesn't require any information beyond the environment itself. So for unseen environments, you would have to, you could generate the training set and train the reward model. But then that's all you would need to do. And if we combined the training sets of multiple different similar environments, which is something we didn't try, but if you did combine that, then I would expect that if the reward model maybe is a little bit larger, then you wouldn't need to retrain it for that kind of thing. It could just have the knowledge for both embedded in its weights.
Looks like we have one more question, and I can answer that. The question was like, is there a tuition or fee for the program? And there is not. Leo and Owen, I wonder if um you'd like to share and wrap up with, if I'm an undergraduate student, I'm thinking about any, in CS, AI, robotics, not just thinking about the Robotics Institute or Scholar Program, but what is your advice for, going forward and like, how can I approach applying for and finding, research opportunities for me in the summer?
I think the best advice I can give is you just have to do it. You never know when things will like how things will play out. Like to be honest, I never expected to get in when I applied, but I
Yeah.
applied anyways. And there's a quote from I think I read this from a like Brazilian writer. He said something like maybe it was not but like he said something like I just did it because I didn't know it was impossible, you know. Uh, and yeah, you just have to apply because I think most students they under underestimate their own potential, and other people like professors and other people like Rachel, they can see the potential on you. So yeah, I'll just say just have the courage to apply, and yeah, just do it.
And
As
I think
far as looking for
that's,
programs
yeah,
themselves, generally just look up whatever school you'd like to work at and look up REUs. And most of them have a website where they kind of disambiguate what programs they offer, and you can just apply there.
that's a great idea. And Leo, one of the things that I was thinking is that we see each other grow through the experiences. I remember thinking about like before we come together and then what we're able to accomplish as a community, as individual scholars. And one of the things that I'm really proud of the scholars and the community is the knowledge that you're able to come out with, that growth, and that so many of the pieces of the program and those outcomes are for you and for your next steps, right? And I think that is really important. So I want to thank everyone for joining us today. And with that, we'll let everyone go for the evening, and we look forward to connecting again soon.
Bye. Thanks for coming.